So I will get started now. Hi, everyone. I'm Anthony. I work as a researcher support for REANS now. And so it's good to see you all. In this talk, in this webinar, we'll go over some of the basics of how you can perform scaling tests using some simple examples and going over some of the basic commands that you'll need to use in order to estimate your job's resource requirements. The webinar is going to be broken into three main parts. First, we'll look at how you break your computationally intensive jobs into smaller scale tests. And then we'll look at using the sacct command to look at the resource uses of these small scale jobs. And then we'll finally look at how you can use the sacct results of your small scale jobs to predict the resource requirements of your larger scale jobs. When you run software in an interactive environment like your personal laptop or your desktop or whatever you're used to using, the software is able to request from the operating system whatever resources it needs from moment to moment. And while you can do some interactive work like this on the REANS HPC through our on-demand service and the applications that we provide there, most of our compute resources are not directly accessible through on-demand in that manner, in an interactive manner. They're locked behind the Slurm queue, Slurm being the queue manager that we use for our high-performance computers. And on a queue-based system, like our HPC platforms, high-performance computing platforms, you must request your needed resources when you submit the job. So that the scheduler is able to make sure those resources are available, and then also so the scheduler knows what's being used and what's going to become available later, so it can queue and stack all the jobs correctly so that there are less wasted resources overall. What this means is that on your personal computer, if your job takes a little bit longer or needs a little bit more memory than you're expecting, that usually won't be a big problem because it'll just pull those resources from the operating system and keep going, so long as it doesn't try to exceed the total amount of available resources on your laptop or desktop or whatever you're using. However, on a queue-based system, underestimating your job's resource requirements will likely mean that the job fails, because you only have the resources available at submission that you request, because those resources are set aside for you and no other resources are accessible to your job. And so unless you're saving the results as you go and you don't need to wait until right at the end of the job, that means you can potentially lose a lot of information, a lot of everything when your job fails, because those resources are potentially just going to be wasted. Most users initially prompted to start using high-performance computers because their local machine can no longer perform the work that they need to do in a timely manner. But the fact that you have to know in advance with relative accuracy as well what resources your jobs will require means that testing the jobs you actually want to run require you to either request significantly more resources than you expect your job to need in order to guarantee it will succeed, or for you to submit jobs that are potentially underestimating the resources and are likely to fail, meaning you have to then resubmit it with asking for more resources that may fail again and have to do that multiple times potentially to get it. And so either way, you're going to be wasting a lot of resources potentially because you're either getting job failures because you ask for too little, or you're just wasting a lot of resources because you're asking for more than you need. And when you request those resources, those are exclusive to you and no one else can use them. And so it's in our interest and in your interest to reduce these wasted resources, because if you ask for more correct requests when you're submitting your jobs, they're going to also queue for better. And though most of our users aren't in a situation where they're paying directly for a subscription, their institutions have some agreement with REANS/NSE where they're getting in a collaborative situation where they're not paying directly. If you are in a situation where you're paying for a subscription and your institution's paying for a subscription, wasting fewer resources means that your money will go further. And so that is where job scaling comes in. So what do I mean when I talk about job scaling? At its heart, scaling is making and running small test versions of your jobs in order to help you predict the resource requirements of your full-size jobs before having to submit them in earnest. The main principle behind scaling being to waste a little bit of time and a little bit of resources at the start of your work, at the start of your project, so that you aren't continually wasting a lot of resources and time later with jobs either requesting a way more resources than they need or unexpectedly failing. So how do you make a small-scale test? The easiest way to create a small-scale test job is to take just a subset of the initial data. Frequently, with HPC work, people have very large data sets, which an analysis or some form of processing or something along those lines must be run on. And by taking a small subset of that data, you'll often be able to run a test job with a fast turnaround time, which scales up in a predictable manner as you increase the size of that data set. And so say you've got, a data set with 1,000 columns and 1,000,000 rows as your full-size data set. If you can maybe just reduce it to be, 1,000 rows or 100 rows even or something like that, and do the exact same analysis. Usually that when you then scale that back up to increasing size of that data, it will grow in a predictable manner so that you'll be able to then use this for your small scale test. Ideally, that small scale test will ideally you'll have been able to create that a small enough test that can run your local machine. The reason that you would like this ideally is because your local machine is a bit more forgiving than the HPC. So if you submit a job on the high performance computer, and as I said, you don't request enough resources, it's going to fail out, and you're going to then have to submit a new job asking for more resources. On your local machine, if you can make a small scale job, even if it runs a while, if you can just get one run, you can use the baseline of how much resources your local machine has. So it's got, 4 cores and 16 gigabytes of RAM as the baseline. And then it took a day for it to run on your local machine, and that can be the baseline starting point for when you run it on the HPC. And then you can run it on the HPC from there. That's usually the easiest starting point. However, it's not always going to be possible for you to do this because you just can't get it running on your local machine, even on small scale. And in which case you will need to do what I said, which is essentially just guesstimate, do your best estimate of how much the resources, the very small scale version of your job will take on the high performance computer, and submit it. And if it fails, increase it until you do eventually get one running. Additionally, subsetting data is not always going to be possible, unfortunately, or provide a significant speed up if you do subset the data. And so some work has relatively small data sets but run many calculations. In cases like that, it may be possible for you to comment out some of the lines of your script so that fewer calculations are being done. However, doing this will generally not be as easy or to use predictively as subsetting data, as subsetting data will generally follow a relatively simple mathematical function without affecting your job runtime, while each line of code is going to do its own thing, essentially, and have its own different processing requirements. This can be somewhat remedied if you have a good understanding of what percentage of the processing and exactly what each line of code is doing. And you can learn about this to a degree by doing some profiling on these jobs. And we do have some support pages that offer information on some of the profiling tools we have available on the high performance computers right now. And we are looking to do another talk in the future on profiling specifically, but we won't go into details here. But this isn't the ideal scenario. You ideally just want to be able to subset data, but if you can't subset data, you may end up being in a situation where you need to try and do this type of work. Also, please note, if I don't seem to be moving on to new slides, do yell out, because it did freeze just recently when I was talking to someone in another meeting. So hopefully it doesn't freeze during this. How large should a scaling job be? As a rule of thumb, you should generally aim for maybe around 10 minutes. Too much shorter, and your job will be spending a high proportion of its time on overheads that are just starting up, loading data in, or loading packages. And then if it's spending a lot of time on overhead, it's just going to be less accurate for these type of scaling purposes. But you don't want to be too long, because these are just tests. You want to try and get good turnaround time so you can get results quickly, so you can move on to running your real jobs. Additionally, as you run scaling tests, some of your jobs may run faster than your initial test job. So while you don't want small scale tests to be so large that they can take a long time, you also want to make sure that even if some of these other scale tests that you run faster, they're still not going to be super short. For this webinar, we're going to use a multi-threaded example, though we do have a support doc page on scaling, which has both a multi-thread example, which is what this one's based off, and then also a sorry, an MPI example, which you can follow through. They are linked to those documents. That documentation page is in the question doc. In this example for the multi-thread job, we're going to use R scripts to demonstrate how you might perform some of these scaling tests. However, the principles of this process apply regardless of what software you're using. You don't need to know anything about R to go through this. It was just used for the purpose of the demonstration. But just as a quick overview of what the R script is doing, it's just going to generate a bunch of random numbers based on a normal distribution and then sum them all together, a whole lot of them, so it takes time. So the script will take a number of CPUs that it has per task from the environment, and then it will run in parallel that many threads. In this hypothetical scenario, the full-size data set which we want to run on is represented by 60,000 iterations of this version of the script, for which we don't know how many CPUs is the optimal amount for running on this job, or how much memory it should be run with, and then or how long it's going to take to complete. And so we want to avoid just guessing and shooting in the dark blind with submitting the full-size job, and we want to try and get a good estimate of how much it's going to need before we submit it, to just minimize the amount of wasted resources and minimize the amount of time that we potentially waste later. The first thing we need to do is to create a small-scale test that is representative of the full-size job and see how long that runs for. And so to do that for this work, as I said, I won't even show you the R script. All I changed inside that R script was literally one point where it said 60,000 to now say 5,000. So instead of doing a 5,000 iteration job, it's now going to do a 60,000 iteration job. It's now going to do 5,000 iterations. The data doesn't matter in this case because it'll be whatever you're doing is what it's supposed to represent. And this is just a representation of us decreasing the size of our data set. And so that's going to be about 1/12 the size of the original data. As I mentioned earlier in the talk, you will want to, if you can, get this running on your local machine when you do it yourself. But again, if you can't, that's fine. Oops. When you write a Slurm script to run this job, the wall time number of CPU cores and the amount of memory you request for the job will ideally be based on how the small-scale job test runs on your local workstation. But yeah, it's not possible, that's fine. Just do that test that I said where you essentially do a bit of trial and error to get it up and running here. And a quick tip that's also worth noting when you are doing this, especially if you're in a situation where you can't do the test on your local machine, is if you can write your script in such a way that it notes its progress, even if it can't give you full results until the end. Just saying, it's done this many tests or whatever, because that gives you, a good idea of how far through it gets when you're doing this test, because it will then allow you to guesstimate how much more time you need to give it to be able to finish when you run it in earnest. For the sake of this talk, we'll assume that you managed to get to create this initial test job and runs with the requested resources as shown here, which is in our Slurm script, which in this case is asking for 1,000 megabytes of memory, 2 CPUs, and runs for 10 minutes. One other thing to note before we move on to the next slide is that I am specifying on this job the Milan partition. The reason for that is that when you're running these jobs, by default on the HPC, it's going to submit jobs to run on both the Milan and the Genoa nodes, the old Milan nodes and the new Genoa nodes. This is usually fine. It means your jobs will queue faster because they'll be able to run on either the older Milan nodes or the newer Genoa nodes, but the newer Genoa nodes are more performant. And so this means jobs will tend to run faster when you submit them on the Genoa nodes. And this is fine if your jobs are asking for enough to be able to run on the slower Milan nodes as well. But if you scale your jobs on the Genoa nodes with the expectation of running on the Genoa nodes and then they land on the Milan nodes, they may not have enough requesting enough time or resources to be able to run on those Milan nodes because they were scaled to work on Genoa nodes, which are more performant, which so it may not have needed as much memory or may not have needed as much time on the Genoa nodes. And so we'll test on the older nodes, the oldest nodes that we intend to run on, or the worst nodes that we intend to run on is the ones that we'll want to do the scaling tests on. Because that way, when we submit them, regardless of what nodes it lands on, even if it lands on the worst nodes that we're intending to run on, it's still going to run. If you only intend to run on the Genoa nodes, you would do only the testing of the Genoa nodes, and that's fine. But if you want to have your jobs run on both nodes, we would advise doing the scaling testing on the Milan nodes, just so that when you estimate the resource requirements of your full-size jobs, you're estimating in the worst case scenario, and you avoid jobs failing. So assuming that we've created that job and we've run it, we will now have some results that we'll want to analyze. And to do this, we're going to use the sacct command. The default output for sacct will give us everything we really need to analyze the jobs if we are running it the same day at the job finished. However, if you're looking back at jobs that are run before the last day, before today, you can use the dash capital S flag, which will then specify the date from year dash month dash day, and then that will show you from whatever that date is as well. When analyzing your scaling tests, the columns which you want to consider are the elapsed column, which tells you how long the job ran for, and it's formatted in hours, minutes, seconds. The alloc column, or alloc CPUs, it's cut off there, but it's just referred to, but it is the allocated CPUs, which tells you how many logical CPUs your job used. Usually you don't need to think about logical CPUs very much. Logical CPUs are just double your physical CPUs. When you request 2 CPUs per task equals 2, you're going to get 4 logical CPUs. I won't explain why, because it's not enabled by default unless you're using hyperthreading or anything like that. You won't worry about it. But you'll just see when you look at alloc, it's going to be double whatever you ask for, but it's just your logical CPUs rather than your physical CPUs. The total CPU column is also required. It will tell you the total CPU runtime of your job. And the max RSS, which tells you the maximum memory in kilobytes of that job, or specifically the processes or the job steps that it's looking at. The utilization percentages of wall time and CPU and memory can be derived from the total CPU and the max RSS values over the amount of CPU time and memory available for the job. But the easiest way to find these numbers is just to run the nnSeth command as shown here. So just this is an example, which will just do those calculations for you. So it'll show you that, you've used 32.8% of the wall time that you requested and 97% of CPU, etc. You'll also notice that each job has multiple rows. So we can see down here, this one's got 3. And these can also have sometimes different values. These rows represent the different job steps or processes for the job. So you should always choose the largest value in any column when considering the resource usage of the job as a whole, because that's the actual one. So it's not the sum of them, it is just the largest of them. Looking at this output, we can see that our test job had a maximum memory usage of about 0.4 gigabytes. In total, the job ran for about 3 minutes and 17 seconds. Though it's worth noting that this is somewhat shorter than the 10 minutes we advise as a good rule of thumb. But we can get away with it here in these examples because these tests have pretty much no overheads. They don't read any data, and they don't load very many packages. I think they only actually load 1 package in. And so there's almost no overheads, and so that's fine for these tests, and it made doing them faster. So now that we have our initial scaling test job, we need to understand how wall time and memory requirements scale with the number of CPUs and data size. The first thing we need to do is to decide what to test first. We can either test how memory and wall time requirements scale with the CPUs, or we can scale or we can do the same test except comparing it to data size. Since these are small scale jobs, it shouldn't matter too much which order we choose. But if you choose to scale the CPUs first, your test jobs will likely finish a little bit faster. While if you scale the data size first, then your jobs will use slightly fewer resources overall. But the end result should be essentially the same for what the optimal resources for your full-size job are. In this example, we're going to scale the data size first. To test this, we'll submit 3 more jobs using 10,000, 15,000, and 20,000 iterations, and then plot their runtimes and memory usage on graphs to better understand their scaling behavior. When submitting these test jobs, it's a good idea to assume that the memory and wall time requirements will scale linearly when you're requesting the larger jobs, and so proportionally increase the amount of wall time and memory you're asking for each of those jobs. In this case, 2, 3, and 4 times more memory and wall time respectively. And it's also good to add an extra buffer of maybe 20% just to be safe. But the job still might fail in these test scenarios, and that's okay. If they fail, you can just submit another one asking for a bit more. Now, I won't show you the S account outputs for these jobs because it's just going to be exactly the same as this one, and it's kind of hard to interpret just looking at S account outputs. And so we'll just move on and take a look at the graphs. But if you're interested in the data itself, the outputs, you can find them in our scaling documentation. Before talking about these plots, I'll just note that I did my plotting in R, but it doesn't really matter where you create these plots and whatever software you want. Pretty much all software is capable of making, or all the software that you're likely to be using, is capable of making simple XY plots, and that's what these are. What we did is we took the values for the time and memory that were in the S account output, and we plotted them against each other, essentially. And the same as any other resources we do later on. They're just simple XY plots. Now looking at our plots, the peak memory usage appears largely unchanged. And so this means that for this example, we shouldn't need to change the requested memory regardless of how many iterations or how big the data size is. So the data size in this case doesn't affect the amount of memory required. That's not going to be standard in most cases for most jobs, because data size is generally, the bigger the data, the more it needs to be written to memory. Just the nature of the way this job works. It's not really real data. It's just a whole bunch of random numbers being created and summed together, is why you see that it's not really scaling. It's just a set amount. However, with regards to the number of iterations, we can see that they are still scaling linearly against the time. So increasing the number of iterations seems to proportionally increase the amount of time it takes. Doubling the iterations doubles the time. And so from this, we can kind of assume or guesstimate that our original data sets of 5,000 was 12 times smaller than 60,000. It's going to take around 12 times longer, which means that since the 5,000 iteration job took about 3 minutes, 17 seconds or something, it's going to take around 40 minutes. And so now that we understand how wall time and memory requirements scale with the data, we need to understand how they will scale with the number of CPUs, so that we can find the optimal number of CPUs that's made our job with. And so we currently are using 4 logical CPU cores, which is 2 physical CPU cores, and which is how you asked for CPUs per task equals 2. But we want to see what will happen when we ask for different amounts of these and how that will scale, so we can see what the optimal number of CPUs is. And so for that, we're going to run these as exact same jobs again, except instead we're going to ask for 2, 4, 6, 8, 10, 12, 14, and 16 logical CPUs, which is the equivalent of 1, 2, 3, 4, 5, 6, 7, 8, essentially. So serial job is down there at the bottom. So let's take a look at these. And again, I won't show you the SAccount outputs because they're hard to interpret, but they are available on the support pages for scaling. So I'm showing two plots here of CPUs versus time, and then the log2 of the CPUs versus time. The reason that we have both is that it can be easier to see the inflection point when you look at the log2 versus time, because a theoretically perfectly scaling job with the log2 job, so doubling the CPUs half the time, you'd see a straight line. And any curve in this line indicates a loss of efficiency or loss of utilization. And so it's more obvious where it's kind of petering out as getting more return on investment, so to speak. Whereas you can just use the logical CPUs or physical CPUs against the time, but it's a bit more difficult to tell at what point you're no longer getting worthwhile return on investment. So looking at these, we can see that increasing the number of CPUs does reduce the return on investment. We're getting less performance increase from doubling the CPUs or increasing CPUs each time. And if we look at how it's bending, this is 2, 4, 6, 8. And so beyond here, it's kind of starting to not be so good. And so 6 or 8 CPUs is really the point where the performance is best here. There's not a hard and set rule about when you should stop asking for more CPUs. If your job needs to run faster, your job needs to run faster. You're on the HPC to run it faster. The only perfectly efficient job is a serial job. And so we don't expect your jobs to be perfectly efficient, perfectly utilize all the resources. Really, it's just about what you need for your work. If your job needs to get done in a more timely manner, you can ask for more resources. But if your job can maybe wait a little bit longer, so it takes a little bit longer to run, but it can be more efficient, please do that, because then it will just save more resources overall. But whatever you need is, yeah, it's going to be a decision that you'll have to make as a user. We could try running the script with more than 16 CPUs, and if the speed up still appeared relatively linear with 16, we might do that to try and get a better curve to kind of guesstimate where the cutoff is going to be. But in this case, it's 8 CPUs seems fine and is a reasonable choice to use for our ideal number of CPUs. Generally, you will want to get the ideal number of CPUs somewhere in the graph. If you can just extrapolate out and do a rule of thumb or eyeball where you think the ideal number of CPUs is. But specifically for the CPUs, it's a good idea to get it in the graph if you can. And I'll talk a little bit more about extrapolating later. Now looking at the job's memory use, we can see that as we increase the number of CPUs taken by a job, the job's memory requirements increase approximately linearly. The behavior isn't necessarily the case for all kinds of jobs, and it's most likely to be the case for MPI jobs. It'll increase linearly because each individual task needs its own set of memory. But in this case, it has increased linearly for these multi-threaded jobs as well. One thing to note about our plot of the CPUs versus the memory is that there seems to be a drop at this 10 CPU or 10 logical CPU point. That's going to just be random variation happening when you do these type of plots. This one in this case can probably be explained by the fact that memory usage, well, and CPU usage and everything, in fact, is only measured at 30-second intervals. It's not measured continuously. And so spikes in memory are potentially going to be missed. This means that so this could have just continually missed in the short amount of runtime that it had the spikes in memory, because these are running quite short. And it's another reason why you potentially want to make sure your jobs aren't too short, because you may end up getting more of these type of outlier data points, which can skew your data. Looking at the memory usage for the 8 logical CPUs, it looks like about 0.75-ish seems to work, probably, of how much resources it's going to require for the job. You don't necessarily need to have the memory in this one. You could extrapolate out for it, especially with it being relatively linear. So in the case of all these plots, as I said, the inflection point or the point of interest is has been included in our plots, which makes it relatively easy, or a relatively easy extrapolation. But if that's not the case, it's relatively straightforward for most plotting software to be able to do some kind of extrapolation. I can't tell you every single software how to do it, but it's a simple Google of extrapolate plot line in chosen software, whatever you're using, R, Python, Excel, and it will probably be able to do a fair extrapolation out from the data points you've added and put a nice line on there that you'll be able to use. But even without doing that, you don't need to fit a perfect regression to your plot. Since the purpose of these plots is merely to something you can do relatively quickly to get a rough estimate of the required resources of your jobs before you run the full-size job. We're not expecting you to be full statisticians or invest a huge amount of time into doing this because we know you need to get your work done. And so just, eyeballing it is often going to be good enough. So we found how many CPUs are ideal to use for these jobs with a speed up after 8 logical CPUs becoming smaller and smaller, where it's not really worthwhile. But why is that speed up asymptotic? One of the biggest reasons why for this nonlinear scaling is something called Amdahl's law. Amdahl's law refers to the theoretical maximum speed up a process can have when it's parallelized. And this comes down to the fact that every single every single parallel job is not perfectly parallel. There's no such thing as a perfectly parallel job. There's always at least some proportion of the job that is serial. And while the parallel portion of the job theoretically might have perfect speed up, doubling the CPUs, half the runtime of the parallel portion, it won't have perfect speed up because there will be other reasons why it's got nonlinear scaling. But even that theoretical perfect situation, the serial portion is going to be unaffected. Or in some cases, the serial portion is going to take longer because when you increase the number of CPUs, you can potentially increase the serial overheads. And so as you increase the number of CPUs for your job, the parallel portions become faster and faster. The serial portions remain unchanged or become slower. And those serial portions become a higher and higher proportion of the total runtime of your job until you get to a point where increasing the number of CPUs, sure, it doubles the speed of your parallel portion. But if the parallel portion of your job is only 5% of the total runtime now, that's not very much. And so this is one of the major reasons why you need to do these type of scaling, because you won't have a perfectly linear scale up. There's going to be a point with every single job where adding more CPUs isn't worthwhile. Another major factor that is especially relevant if you're running MPI jobs is that there are communication overheads between CPUs. And the more CPUs your parallel job has, the larger amount of compute time that just goes into managing that overhead, that communication. In fact, it can get so large, the communication overheads, that adding more CPUs can actually decrease the speed of your job because the communication overheads for adding those CPUs, because every CPU potentially has to communicate with every other CPU, can be bigger than the extra speed up for having more CPUs. And so, the only thing worse than adding more CPUs to your job and getting no speed up and wasting resources and having longer queue times is adding more CPUs to your job and having it slow down and having all those other problems be worse. And so for both of these, you want to do scaling tests, but there's going to be a whole lot of other reasons as well for these nonlinear scaling, but these are 2 of the major ones. And so now that we know approximately our job CPU, full-size job CPU and memory requirements and wartime requirements, we can try to estimate the total resource requirements of our 60,000 iteration job. And then from this, we can estimate that it's needs about, for an 8 logical CPU or a 4 physical CPU job, it's going to need about 0.7 gigabytes of RAM. And it's also going to need about 21 minutes because it's going to be, since the 8 CPU 5,000 iteration job took 1 minute and 45 seconds, 12 times that goes to about 21 minutes. We'll also be on the safe side of it and ask for about 1,000 megabytes of memory, and we'll change it to 30 minutes, which is, it's not exactly 20% more. It doesn't have to be exactly, it is just a rule of thumb. But yeah, just as an idea, you've asked for a little bit more and you would run it asking for a bit more. And so now that we've gotten that to this point where we have a full-size job that we feel relatively confident in our estimate, we'd submit it and we'd see what happens, and hopefully it runs. And then if it does run, we can then take a look at the final job. And in this case, the estimates we came to was accurate, or relatively accurate, that is. It took 20 minutes. The memory was a bit cutting it close. So it used just barely under 0.75 for the, so if we had stuck with the original estimate of 0.75, we could have potentially gone over with those, 30-second intervals. It may have potentially spiked above 0.75 at that point. Just another reason why you want to, ask for a bit more than you actually expect. And now that we have a full-size job that has run, we can essentially use this as our baseline to determine the future full-size job. So if this had turned out to be an overestimate in anything, we could then reduce those when we're running those full-size jobs later. Though, as I said, we still want to be asking for more than we actually expect, as a rule of thumb for memory and wall time being about 20% more. You don't want to ask for more CPUs than you expect, because CPUs, there's an optimal number of CPUs, whereas wall time and memory are a maximum amount type scenario. Then this webinar, I just went over the example using multi-threading, as I said, using the multi-thread example, but there is the MPI example that's available in our documentation that you can go over if you're interested in looking in that. And so now I will move on to questions.